Testing, can you hear me? Okay, this video is public now. So I'm going to be streaming calculus again. I took a long gap. Like I didn't study calculus for a while, so I may need some revision. So last stream, I studied about line integrals. So basically with line integrals, what I remember is I have a graph. Z, X, Y. I have this A over here, B over here. I have a function like f of y, like z is equal to f of y, some function over here. If I want to find the area of this sheet, then I would basically do this from A to B, f of y, dy. If I have CD over here and I have a function g of x, I want to find this area, I would do from C to D, g of x, dx. But here's the issue. What do you do if 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 instead of having the interval over here or over here, what if your interval is by interval I mean the um, place where you're integrating at? What if it's this line? What if it's a curvy line instead of on the x-axis or the y-axis? What if the place where you want to integrate at is a curve in the xy plane? So let's say we have f of xy with this domain, and f of xy is like this function over here. It's like some function over this curve, and we want to find the area of this sheet. So how do we do this? Let's say this point is AC and then BD. Actually, let's just do AB. AB, CD. And let's call this curve C. So we want to integrate over curve C. So how do we do this? First, let's say, let's focus on curve D first. This is the xy plane. Let's say the curve is defined by a vector. It's defined by the path a vector traces, a vector value function. So we have a vector value function, RT, which is defined as P, XY, PQ, XY. Is it, wait, no. Like this, maybe. This is a vector valued function, and the path it traces gives this curve. We want to find this integral. Suppose, yeah, if you want to find this, and suppose f of xy is defined like so. Hold on, no. And let me think. So f of xy is a function. This curve is defined by the vector valued function rt. So the integral notation is like this. ds is like the instantaneous change in the curve when you increase t. ds is like the change in the curve for the instantaneous change in t. This would be equal to integral from point A. Wait. Let A be at t is equal to t naught, and then CD be at t is equal to t1. So this here is AB, but let's call it t naught, and then all the way till here t1. So from t naught to t1, if all the RT values where we evaluate it, and then you multiply it, the modulus of the derivative dt. This is equal, this is how we evaluate the function. And a shorthand notation for this is, I think it's like this. This I have to revise. There is another notation for this. No, not for this, maybe the vector one. So let's see. Line integrals. Let's see if I have made a mistake somewhere. Yeah, that's how they defined it. So from A to B, where T goes from A to B, we evaluate f of RT and then the modulus. We do two lines, right? The modulus of a vector. So that's a scalar line integral. But there is also a vector line integral. So for a vector line integral, suppose we have a vector field, suppose capital F is a vector field So for each point xy, it gives like a particular vector at that point. So p xy u xy. So f of f would be a vector field. So every xy value it gives a vector. And then actually I'll just color it to differentiate between from RT. So we have this. Let's put some difference. So all of these vectors, so fxy, capital Fxy defines these vectors. And then we have this and we have RT, of course. So a vector line integral from t naught to t1 is like we add infinite sum of this dot this. So we add infinite sums of f at RT at that particular value dot RT. Is this correct? Yeah. Dot RT. Or maybe it's the tangent. Sorry, yeah, it's the tangent. It's this, the derivative of RT. And we do this infinitely. Is this correct? Yeah. I think I got it. So so basically what happens is suppose RT is going from here to here, but then as it's going, we have a tangent line, we have a tangent vector over here. This tangent vector is like the change in RT for small changes in T. So this tangent change in RT or instantaneous change in T. So this over here, this over here. So we are doing this dot dot the vector yeah dot the vector field at that position, which could be pointing at anywhere. So tangent dot this, we are doing like infinite sums of these throughout the entire line, times it and multiplying it with dt. That's the vector line integral. Let's see. Yeah, f at rt times the derivative of r dt. That's the two main topics I learned in this chapter. And there was another one called flux over a curve, when instead of tangent, you're doing the dot product with the normal vector. So the vector field, times the normal vector for all of these points. I think they call it the flux. Yeah, the flux over a line curve. Hold on, I need to check something. Okay, sorry, that did something. Okay, so now we are going to study about conservative vector fields. So basically, if I have a 3D graph, any 3D graph, 3D calculator, f of um sine x plus sine y. Okay, yeah, let's use this graph. Plus 2. Yeah, for a 3D graph, I can have so a vector field, conservative vector fields. Wait, I need to go back. A vector field is like the derivative of the graph, the gradient of the graph. So f of xy is some 3D graph, some 3D graph defined over here, right? Let's just should I do this? Maybe extend it a little bit. I'm just drawing the boundaries. Maybe forget this. I'll just draw it here. Maybe never mind. So suppose I have a 3D surface, this, and then like this, then like this. Some 3D surface defined by f of xy. And we have the gradient of f, which is basically a vector which is a partial derivative of x in the x direction, partial derivative this in the x direction and this in the y direction. So for example, I take this point over here on the surface. We have partial derivative in the x direction, and partial, like let's say the gradient, let's say the change in f is like going downwards. F is decreasing for instantaneous change in y. F is slightly increasing for instantaneous change in x. So a combination of these two vectors would be something like over here. Sum of these two, yeah. So this over here is an example of gradient of f. This vector is defined all over the surface and it's the gradient of f. It's also written like, also write it like this. And now here's the thing. If I give you a function and if I give you a vector field, so this function over here is a vector field because defines a vector for every xy value. So we can portray this in the xy plane. So for example, here's this xy plane is over here. And this thing is over here, let's say. Over here. And all these three vectors are parallel to the xy plane. So this is parallel to this is parallel. This is like the sum of these two. And like wait, I think this should be decreasing, right? Because it's going down. Yeah, because yeah. This should be negative because f of is going down as y increases. So this should be increasing here. So I can draw this on the xy plane itself, and each vector on the xy plane, so every vector gives the gradient of f. Gradient of f at this xy point, gradient of f at this xy point, gradient of f at this xy point. Remember, like functions are 1 to 1, right? So for each xy combination, there is only one f value. So we can write this on the entire xy plane. So we can like draw all of these vectors in one plane. There wouldn't be any overlapping because it's like you can't have two f values for one xy pair. Yeah. Now here's the thing. If I yeah. So this is a hold on. So this is an example of a vector field. Sometimes it's drawn like this. So f over here is the vector field. So capital F is the vector field of small f. But if I give you a random out of nowhere vector field, so f is so let's use G. If I give you this vector field, and would you be able to figure out the original function, which has this vector field? Like, would you be able to find a vector function g of xy, such that the gradient of f is this vector field? If such a function does not if such a function does exist, if there is a function g of xy such that the gradient of g of xy gives this vector field, then this is called conservative. This is called conservative. And for this conservative vector field, the associated function is called the potential function. So for a for a vector field, if there is a potential function, then this vector field is called a conservative vector field. If there is no potential function, then this is not a conservative vector field. It's like integrals. You can find, you can integrate a function and find the original function back. Like you can integrate the derivative of a function, get the original function back. But the problem is you don't know the plus c value, right? So this surface over here, maybe like this part is over here is at 2. If you get the original function, so starting with the vector field, if you try to get the original function back, there will be a plus c value. So you don't know where the surface is, but you do know the gradient of the surface. This tells you the gradient of the surface, but if you get the original function back, you don't know the plus c value. Yeah, there would be a plus c value. So anyways, a conservative vector field has a potential function associated with. If no potential function exists, then it's not a conservative vector field. Let me see if I'm correct. Imagine if I say all that and small f is called a potential function for f. Yeah, if the gradient of small f is capital F. And the gradient is defined like this. Where did they mention the conservative? A vector field, capital F, is a conservative vector field or a gradient vector field if there exists a scalar function f such that gradient of f is capital F. Okay. So now we can actually start the chapter. So curve C is a closed curve. There is a parameterization such that the parameterization traverses the curve exactly once and RA is equal to RB. Okay. So this is a closed curve because if RA is over here, we go all around the curve and then RB goes back to the same position. Curve C is a simple curve if it does not cross itself. Okay, this curve is also simple because it doesn't cross. This curve crosses, so it's not simple, but it is closed. Determine whether a curve is simple and closed. So we have this function over here. RT is cos t sine 2t over 2. Can I? Cos t sine 2t over 2 and from 0 to 2 pi. I get this. So it's not simple because there is like an intersection, but it is closed. Closed but not simple. A region D is a connected region if for any 2 points P1 and P2 there is a path from P1 to P2 with a trace contained entirely inside D. So this is not connected because if I have P1 over here and P2 over here, I cannot draw a path that is entirely inside the region. Region D is a simply connected region if D is connected for any simple closed curve C. That lies inside D. Any simple closed curve C that lies inside D. And curve C can be shrunk continuously to a point where it's staying entirely inside D. In 2 dimensions, a region is simply connected if it is connected and has no holes. I don't understand their previous definition. Okay, so I think if I draw a curve like this, and inside the region and shrink it as much as I can, it will still be inside the curve and it will still be inside the region. If I have a curve like this and try to shrink it, then the curve at some point will not be inside the region. I think that's what they're saying. If D is connected for any simple closed curve C that lies inside D, and curve C can be shrunk continuously to a point where it's staying entirely inside D. Fundamental theorem for line integrals. We now understand some basic curves and regions. Let's generalize the fundamental theorem of calculus to line integrals. Okay, so according to the fundamental theorem of calculus, when we integrate the original function, we can use the derivatives. The derivative at the endpoint. We can use the antiderivative at the endpoint. So they're doing something similar for line integrals, where if we have the gradient of f and we integrate it, we just need the endpoints of the original function. So this is like this by the chain rule. So the derivative with respect to t is the gradient f dot the derivative of r. By the fundamental theorem of calculus, we have this, we have this. And this is from A to B. Okay. Applying the fundamental theorem. Exercise 6.29. So we have a vector field. Do x ln of y. X squared over y plus c squared. Do y c. And then rt is t squared t t. 1 to e. So 1 to e. So what are we trying to find? Without using fundamental theorem of calculus and then using fundamental theorem of fundamental theorem of line integrals. So they want us to integrate from 1 to e f dot rt dt. If we did use fundamental theorem of line integrals, what would we get? Of all f, no wait, this is the, sorry, it's the other one. It's this. F of rt, we have 2x. But if we are using the parameterization, then we would write t square, 2t square ln t. T square over t. Wait a minute. T square over t plus t square. Two yc, 2t square. And this is equal to 2t11. Yeah. And then if you do dot product, uh, No, wait. This is x square, right? So t square here, over here will be t to the power of 4. So this is t cubed. This times this 4t cubed plus it with t cubed plus 3t square. I want it from here to here. Um, take the original function, right? Yeah, we need to find the potential function for this. Gradient of f is equal to f. So we have um if I write this, then the gradient of f, the partial derivative with respect to x, would be 2x ln of y. Partial derivative with respect to y would be x square over y. X square over y plus z square. Partial derivative with respect to z would be, yeah, 2yz. So this is the, yes, yes, yes. Then if we do this over here, we have t to the power of 4 ln of t plus it with t and t square t to the power of 3. Or 1, it's just 1. Ln of n is 0, right? Ln of e is 1. So minus 4, 3, 1. This is without the theorem of line integrals. Okay, so they got this answer. But if they did it without the sorry, this is with the theorem of line integrals. If they did it without the theorem of line integrals, we get this. Yeah, it's this, right? Plus the, yes. So 1 to e. Yeah, this part is the confusing part. For t cubed ln of t integral requires integration by part. All right. The fundamental theorem for line integrals has two important consequences. The first consequence is that if f, capital F, is conservative and C is a closed curve, then the circulation of f along C is zero. That is, this is zero. See why this is true. Let f be the potential, small f be a potential function for capital F. Since C is a closed curve, the terminal point Rp of C is the same as the initial point. Therefore, by the fundamental theorem of line integrals, this is equal to 0. Let capital F be a vector field with domain D. The vector field capital F is independent of path if this integral with the line integral with curve C1 is equal to line integral with curve C2 for any path C1 and C2 in D with same initial and terminal points. Wait, would the fundamental theorem of line integral work if the vector field doesn't have a potential function? What happens then? Do we need to do it the traditional way? Do we need to do it like without using the theorem? It's independent of path if curve 1 is equal to curve 2 for any paths C1 and C2 in D with same initial and terminal points. Yeah, I think what they're saying is you have same starting point, same end point. You have C1 and then C2. So, but according to the fundamental theorem of line integrals, it's supposed to be for any curve, it's supposed to be equal, right? Okay, but what if f is not conservative, so a potential function doesn't exist? Therefore, we use this. So f is some vector field which may not have a potential function. If this and this are equal for any for any curve with the same endpoint and the terminal point, if the integral is equal, then we say f is independent of path. If capital F is a conservative vector field, then f is independent of path. Okay, that makes sense. Showing that a vector field is not conservative. Use path independence to show that vector field f is not conservative. Wouldn't it be easier to show like the cross parity property? So what do they do? Never mind. Conservative vector fields and potential functions. Given a conservative vector field, how do we find a function such that gradient of f is equal to... Okay, so how do you find the potential function? Before giving a general method for finding a potential function, let's motivate the method with an example. Find the potential function for f, thereby showing that f is conservative. Okay, let's Example 6.31. So f is equal to 2xy cube 3x square 3x square y square cos y. So we have this. Then what? For f, so let's assume f exists, then the gradient of f, sorry, let's assume f exists, partial derivative of x is equal to this, partial derivative of y. What is this? Partial derivative with respect to z. That means if f is equal to x squared y cube, derivating with respect to x would give this, derivating with respect to y would give this, derivating with respect to z would not give this. This is the issue. Oh no, wait, I got it wrong. It's 2 dimensions. Derivating with respect to x gives this, derivating with respect to y gives this part, but not this part. So let's see. Derivating sine y gives cos y, but with respect to x, yeah, this will disappear. And the c will disappear in both cases. So we have square y cube sine y and then plus c. Plus c is the general. Find one potential function. Okay, c is equal to 0. That's a potential function. Determine whether the vector field f is conservative. So if x y square z x square y z z square. So let's say f exists. The partial derivative with respect to x would be, with respect to y would be, then with respect to z would be. But then if we take this and then derivate it again, with respect to y, we get to x, y, z. Then do this, do it with respect to x. Sorry. Get to x, y, z. Okay. We take this, derivate with respect to z, then x, y. Then if we take z derivative with respect to x, we get 0. If these two are not equal, then no potential function exists. If a potential function did exist, if some function did exist, then f of xc should be equal to f of cx. Yeah. Right. Okay, I will end the stream here. And then next stream I might study some other book. So see you guys next time. Bye.